guys, Miss Brumwell here. We're going to move to section 1.4, and we're going to throw in some trig functions, exponential functions, and log functions into what we've been doing with limits. Okay, so here's some just common trig limits that we want to commit to memory. Basically, sine and cosine are both great ones for just using substitution. So when I substitute in 0, sine of 0 is 0, cosine of 0 is 1. So those are two that show up a lot. These ones, if theta is measured in radians, the limit as theta approaches 0 of sine of theta over theta is always going to equal 1. Same thing with its reciprocal. And then if we throw a coefficient on there, my limit as x approaches 0 is going to equal that coefficient. And then if I have coefficients in both the numerator and denominator, I'm going to get that ratio of coefficients to be my limit. And then this is another one that's going to come up. Cosine of theta minus 1 over theta also equals 0 as theta approaches 0. Okay, so let's use some of these in practice. Okay, so first I'm kind of like looking, does this match any of these over here? So this one is very close to that top one, but I have a 3 in there, right? So it actually follows this guy. So it's going to equal that coefficient. I'm going to kind of show you the longhand here as to why. But basically this should equal 3 if I can apply this rule. Okay, so basically we have, if I were to multiply by 3 over 3, so I'm really just multiplying by 1, this is going to turn into the limit as theta approaches 0 of 3 sine of 3 theta, sine, that's sine, over 3 theta, right? We multiplied the top and the bottom by 3. Well, if these match, then that follows this, right? The arguments are the same. So I'm going to say let t equal 3 theta. So as t approaches 0, theta is going to approach 0. Okay? So basically, I'm going to rewrite this as the limit as t approaches 0 of 3 times sine of t over t. Well, this part equals 1. So this is going to turn into 3 times 1, which is 3. So that's kind of why this one works. It's derived from this original one. Okay? All right. Well, this is kind of the same thing. Again, I'm going to kind of show this one longhand, but this one is going to follow this limit. So I've got two different coefficients. It should result in the ratio of the coefficients. So it should equal 5 over 2. Again, I'm going to show it to you longhand here as to like why. So I'm going to divide both of these by theta, and you might be like, why can we do that? It's just reducing a fraction, right? When I reduce a fraction, I'm dividing the numerator and denominator by the same thing. So division, as long as I do the same thing in the numerator and denominator, is a legitimate algebra move. So we now have the limit as theta approaches 0 of sine of 5 theta over theta, and then over sine 2 theta over theta. And then basically this turns into this twice. So I've got the limit as theta approaches 0 of sine of 5 theta over theta, divided by the limit as theta approaches sine of 2 theta over theta. So then I can multiply this whole one by 5 and have exactly what we had over here. So we know that this limit is going to equal 5. And then this one's going to equal 2. So that's where I get the 5 halves. All right. Okay, verify. Back to your trig identities. Verifying. Okay, so they are asking us to verify that this one is true. Okay, so we're going to show like why is this true. Okay, so I'm going to do the limit as theta approaches 0. I'm just going to rewrite it here. Okay, so you guys might remember a common practice when we were verifying trig identities. When I had something like this, if I multiplied by its conjugate, that would a lot of times help me out. So if I were to multiply this, the other reason is one of the most common identities we use, I'm just going to remind you what it is. Okay, is cosine squared plus sine squared equals 1. That one's going to come into play a lot. So if I get cosine squared in here, that might be helpful, and I have a 1 involved. So there's some relations that are going to be helpful. So I'm going to multiply by cosine theta plus 1. And again, I'm going to do the top and bottom the same, so I'm really just multiplying by 1. I'm just going to change how it looks. So this is difference of squares when I put it together, right? I got to keep the limit here this whole time, limit as theta approaches 0. When I multiply these, I'm going to get cosine squared minus 1. And then I'm just going to leave this theta times cosine theta plus 1. Okay, well, this is really like part of this, right? If I were to subtract 1, so I get cosine squared theta minus 1, and then I subtract sine squared. So I move the sine squared, I move the 1, they basically switch places. Here's what I would have. So this is the same as this. So we've got the limit as theta approaches 0 of negative sine squared theta over the same piece. Okay? All right, so now this fraction multiplication I could break into two things. Why I'm seeing that is because I can kind of see this is in there somewhere, right? Sine squared is made up of two sines being multiplied, and then I have theta in my denominator. So I'm going to rewrite this guy, come up here, as the limit as theta approaches 0 of sine theta over theta times negative sine theta over that cosine theta plus 1. So I just pulled this apart into two fractions. I did that strategically because I know this is 1, right? That's one of those ones we just kind of commit to memory. So this is 1. And then I'm going to try using substitution. I'm going to try to plug in 0 here, okay? And this is times. So I'm going to say, if I know that's 1, times, okay, if I plug in 0, negative sine of 0. Well, sine of 0, 0, negative 0, still 0. 0 divided by anything is 0, and cosine of 0 is 1. So I really get 0 over 1 plus 1, which is 1 times 0, which is 0. So we just verified that this is true. All right. Now let's look at log and, don't need this, sorry, this was only supposed to be on that other page. Okay, now let's do some logs and exponentials. All right, so basically exponentials, especially because they're continuous for every real number, they are easy. I just substitute those values in, okay? Now for logs, it's really important that those values are positive and greater than 0, right? Can't be equal to 0, cannot take the log of a negative number, but otherwise we can substitute. Something just to remember about the exponential function. So it looks like this. Okay, so as I approach negative infinity, so as x goes to negative infinity, e to the x goes to 0, but remember it doesn't ever hit 0, but it gets really, really close to 0, which is that limiting value. As x goes to positive infinity, well, my graph's shooting up to infinity, so that's why that one equals infinity. And then as x approaches 0, so remember we always do have that y-intercept of 1, so the limit as x approaches 0 approaches 1. Now for natural log. Natural log looks like this. Okay, so as I approach 0 from the right, I can't approach it from the left because there's no graph over here. So as I approach 0 from the right, my graph shoots down to negative infinity. As I approach 1, so x is 1 is where I have that intercept. Some values there. As I approach 1, my y value goes to 0. As x goes to infinity, this log function also is gradually going to increase forever to infinity. All right, so now we're going to use a couple of these. We're going to show that f of x equals e to the 2x is continuous for all real numbers. Okay, so basically we need to meet those three cases again, right? It's continuous on that interval. Okay, so first, domain. Okay, well, all real numbers is the domain. So, is domain of f of x. So that one checks out. It's in the domain. Case 2, the limit, okay, does it exists. Okay, well, any value I put in, because it's defined for all real numbers, I'm just going to plug it in. So the limit of, I'm just going to call it f of x, is going to equal whatever I plug in, which is going to be f of c. Okay, and then does the limit equal that? So we are going to look for, well, let's actually find the limit, I guess. So we'll do this. Okay, so this would equal e to the 2 times c. So the limit as x approaches c of f of x is the same as f of c. So kind of those two things together meet that third condition. So f of x is continuous for all real numbers. I guess I don't need the word all in there. Okay? All right, this next one. Okay, so I could kind of think of this as a composition of two functions. So I'm going to kind of break this apart. So I'm going to say that this is the same as g of f of x. Okay, where g of x is the cube root of x, and f of x is natural log of x. All right, so let's look at where those are continuous. Remember, root functions and natural log functions are continuous on their domains. So what's the domain of this one? Okay, well, g of x is continuous on its domain because it's a root function. And cube roots are all reals. Okay, on domain of all reals. Okay, f of x is the natural log of x. So the domain of natural log of x is anything greater than 0. So it is continuous on its domain. And here's the domain. It is x such that x must be greater than or equal to 0. Okay, so when I compose these two, we're going to take like the most restrictive of these. Okay, so all real numbers not restrictive, this is restrictive. That's going to be the domain and the continuity interval that the composition takes on. So f of x is continuous on its domain which is x greater than or equal to 0. All right. Okay, that is it for this video, guys.